All right, so welcome everybody. You've made it to the last session. Hopefully everybody survived the MOU notebooks on their computers. I realize those take a really long time to run, and that's sort of the nature of the beast with global methods in general. So welcome to the world of global methods. Before we get started, there is a survey. I think Rui posted that in the chat for the class. It'd be great if you guys could give us just a little bit of feedback. It's super short, just a couple questions, I think, just to help us understand if this sort of hybrid learning format was what you were expecting, or if you needed something different or more or less. That would help us. And as always, if you have any questions, please drop those into the Q&A. We can also review questions from previous sessions. If you have something we didn't cover last time that you had a question about, feel free to bring that up also. So today is all about optimization. Optimization is something completely different from what we've been doing so far. So up until now, we worked on setting up our PEST interface and getting ourselves ready to do data assimilation, what we call calibration, some uncertainty analysis. In the typical modeling project, once we get to this stage where we have our posterior ensemble, traditionally we would go into sort of scenario testing mode. There would be a lot of sort of what if questions. What if we pump the wells this way? What happens? And the modeler goes away, runs the ensemble and says, here's what happens. Or what if we operate the pump and treat system this way? How does that affect concentrations? Modeler runs the ensemble. Here's how it affects concentrations. Optimization takes that, I think, to another level, even flips it around and says, okay, if these are the things you think you can have control over in terms of pumping rates or injection rates or drilling new wells or whatever, and these are the things you don't want to happen, this is the optimal way to operate, or this is the optimal way to make those choices to maximize the beneficial use of the system while avoiding the bad thing from happening. And that's the standard sort of description of an optimization problem. There's some terminology. I guess you guys saw that at the top of the opt notebook. There's still input quantities to the model. There's still output quantities to the model. We still use the PEST interface to interact with the model. But where we had parameters before, where parameters are uncertain quantities that relate to some characteristic of this aquifer system or the forcings that run into it, we were really concerned about the statistical distribution of that quantity before we did history matching, after history matching. Is it biased? Is it too narrow? Blah, blah, blah. Now we have decision variables. Those are those model inputs that humans have some control over. And no longer do we care about the prior distribution, the posterior, the bias. In fact, if all the decision variables go to their bounds, that's, in some cases, that's a perfectly legitimate solution to an optimization problem. So decision variables, we care a lot less about their statistical distribution. We just need to manipulate these things to seek this optimal objective function. And so that term objective function that we use in data assimilation, that's actually because those data assimilation algorithms that we use are in fact optimization tools. They're just what we would call bound constrained optimization problems, in that the only constraints in those problems are the bounds on the parameters. So an objective function is simply a combination, a nonlinear combination sometimes, of the decision variable values, and we want to either maximize it or minimize it. And then on the other side of that, there's these things called constraints. In the Freiberg problem, we were concerned about surface water groundwater exchange. That was our forecast. It was a quantity that comes out of the model. It's uncertain because parameters were uncertain. Constraints are kind of the same thing, right? We'll see today, you saw in those notebooks, we used surface water groundwater exchange flux as a constraint instead of as a forecast. So we said, okay, whatever we do to the groundwater pumping rates, we want to make sure the surface water groundwater exchange stays a certain direction so that the stream is either always gaining or at least not losing. And so we set that constraint that flux couldn't change sign, and the river system, the SFR network, couldn't give water back to the aquifer. So that was our constraint in that problem. Do we have any questions about the high level concepts related to optimization problems? If not, I'm just going to scroll down to that money figure on the first optimization notebook. Oh, I should mention also, I recruited Cecile to help today. Cecile's a colleague of ours. She's really good with optimization problems, and so hopefully she will have some very informative comments to make about the nature of these optimization problems. And I've also asked her to give us a little bit of a synopsis of her learning going through these tools and self-teaching around uncertainty analysis and data assimilation and optimization. So we'll get a little bit of that from her towards the end of today's session. Okay, let me share my screen real quick. There we go. So everybody can see that figure. So this figure is showing both the decision variables on top and then our constraints on the bottom. So we said for those last 12 stress periods, the ones that were sort of the future conditions where we hadn't assimilated data, we were going to treat the pumping rate in all of our pumping wells, I think there are 7 of them, as the decision variables. So every stress period, we can change the pumping rate of every pumping well. And our idea is we want to maximize how much groundwater we can take from the system while not causing the surface water groundwater exchange pattern to reverse, so that the SFR network isn't being drawn down by our groundwater service, but by our groundwater use. Right. So on top, we see stress period. This would be the first one. It starts at 13, 14, 15. And each one of these bars shows you the maximum rate of each one of the pumping wells, and then what was the optimal pattern for the well. And then over here in the well ID, that's the layer row column, zero-based, of course, of where the pumping wells are located. And then down here on the left axis in blue, that's the total extracted groundwater rate, the aggregate, by summing up all the pumping wells together. And then on the right axis in purple, that is the surface water groundwater exchange flux as simulated by the model. And so what we see is as we're coming along, remember there's a dry season that happens right in here. The optimization problem says, okay, guess what? We have to turn down the pumping rates, because if we don't, we're going to drive the surface water groundwater exchange to be a losing system. And so it perfectly brings down the pumping rates till it gets right on the constraint here, which is the minimum amount of water we're willing to accept for beneficial use. So we can't go less than this because maybe the town doesn't get its water that it needs. And so it comes up to this rate during the dry season. Everything just kind of works because we designed the synthetic problem so that everything would just work. And then we come out of the dry season, the pumping rates go back up. Does everybody see how that's working? So you can see there's a pretty cool pattern that emerges up here in terms of what is the optimal way to operate each one of those 7 wells as you come into a dry season. And it's not entirely intuitive, just thinking about that here you have these 2 wells are happening together, and the next stress period you've turned one of them down almost to 0, one of them halfway down, and then the next stress period, the one that was almost 0 is at full and the other one's gone. And so there's this weird pattern. And that's because the optimization problem is using the aquifer storage and also the spatial orientation of where the wells are and where the SFR is to get the water that it needs, to get as much water as it can, while also keeping our surface water groundwater exchange flux in a happy place. Any questions about that? I can't see the Q&A. Are we good to go, Rui? Okay. Sweet. So that is standard deterministic optimization. But then you should be asking yourself, well, what was the point of all of that uncertainty analysis, right? Why did we go through and do all this ensemble business if we're just going to disregard that when we start to do our advanced scenario testing? Say, well, we can bring the ensemble into the optimization problem through this idea of chance constraints and chance objectives. I'm sure you guys have seen some of this before, but the idea is, here's our distribution, right? For some, let's say this is a dewatering problem. And the idea is that maybe the dewatering problem has to draw the water level down to 19. And so we run our model with our ensemble, and because, hydraulic connectivity is uncertain, storage is uncertain, etc., we don't just get 19, we get a range of values. Some of them are at 19, some are less, some are greater. Well, if we want to be risk averse, if we want to make sure when we go to the site and we start dewatering that we're actually going to get to that value of 19, we have to overpump, right? We actually have to draw the water level down lower so that we have some statistical confidence that we will actually achieve at least 19, if that was our objective. And so you feed this sort of ensemble from the UQDA world into the optimization world with something called, they just call it a stack. It's the same thing. It's a parameter ensemble. And so both PEST PPOpt and PEST PPMOU can make use of that same file and queue up those runs for you and process those runs so that you can get this risk flavor when you start to do optimization under uncertainty. So I'll just show you quickly. This is the Opt2 notebook, which hopefully everybody ran. Here's the same figure, but what we're showing here, this is the actual simulated surface water groundwater exchange and our constraint value is this purple dashed line. And so you can see we're no longer right on that line. And the reason we're not right on that line is because this is what was actually done with the model, but what the optimization problem saw was actually a shifted value. And so the width of this purple bar, that's how much water we had to leave going into the surface water system to be statistically confident that we weren't going to reverse the sign and have a losing groundwater system during the dry season. And so again, the way the optimization problem attacked this, you can see this is our minimum production rate. We can't go below that. So what happens is if you look here, like at stress period 18, here we're at 4,000. In the other problem, stress period 18, we were closer to 6,000. So what the optimization problem again is doing is making use of storage in the system. So it starts turning down the pumping rate earlier so that when we get to this critical period, we maintain a statistically significant amount of surface water groundwater exchange and maintain our constraint value. Everybody good with that?
There's a question from Tariq.
Okay.
In the first opt example, you set your decision variable to 0 initially. Why? And would it make a difference if you set them to something else? If instead of maximizing the objective function, I wanted to minimize it, would I do the reverse? That is, set the decision variable to the maximum, some maximum.
That's a really good question. So I set those to 0 for their initial values to make sure we were well within the feasible space. Because the way this simplex algorithm works with linear programming, it works really well if you start inside the feasible region and it can quickly find itself on a constraint and sort of crawl along that simplex. If you start largely infeasible, sometimes that can give it problems, especially when you're evaluating that response matrix. So I wanted to make sure I was in a feasible space to start with. And that's the reason I started with those at 0. And if everything's linear, it shouldn't matter. You can start with any numbers you want to if everything's linear. But I think if there's any sort of nonlinearity in the system as well, it's good to start well into that feasible space.
And another one from Tariq. The formulation of the objective function in the first example is relatively simple. Does PyMU facilitate formulating more complex objective functions, and will a more complex objective function affect the SLP performance?
Yeah, that's another good one. So this is all this SLP with the linearity assumption. So what we did in this first example, our objective function was it's dreadful equation, but it's just a sum of all the decision variable values. And we said if we sum up all those multiplier parameter rates, we just want that number to be as big as possible. You can feed OPT an observation name as its objective function. So you can say use this row of the response matrix as the coefficients for the objective function. So you can do that trick. But again, OPT will only tolerate very mildly nonlinear optimization problems. If it's anything more than the slightest nonlinearity, it's going to give OPT trouble. And that's when sort of MOU comes into play then, or another tool that we're working on that's sort of a middle ground between those two. I think Cecile had something she was going to talk, or I don't know, put her on the spot, but she can talk about the nonlinearity of this problem. Because if you look down here, you can see there is a little purple bump, right, that goes above that constraint value. And so Cecile and I were talking about this the other day, and what she figured out is that is a nonlinearity problem. So if you do 2 iterations with SLP, see, where do we load that up? Let's see if I can find it. So up here, if I change that from, if I do 2 and then I have the 2 files available, I get it snaps onto that line a little bit better. So there's a little bit of nonlinearity, even in this simple inverse problem, and it's probably coming from both SFR and the water table formulation that we're using. That sometimes can be enough just to bring some nonlinearity into the relationship. Did I get that right, Cecile?
Yeah, that's what I found too. I found that using sequential linear programming, and not max value greater than 1, in general gave me better results than just sticking to linear programming, so NOP max equal to 1, because the optimization problems we're working on are generally not linear. So yeah, sequential linear programming was better.
Thank you. Awesome. Any other questions from anybody about this stuff?
There's a couple more.
Okay.
From Tariq. He's all over this. In the second ops example, when we bring in risk shifting, are there any a priori data from your original UA stack to indicate if certain levels of risk are feasible, or is this too dependent on combination of decision variables plus constraints?
So that's another really good question. So down here at the very end of the notebook, we actually rely on just the linear programming trick. We can quickly run through the problem and start to understand where feasibility falls off. And I've seen this chart before where right when you get to about 0.55 or 0.6, it becomes infeasible, which means that even in a linear sense, the feasibility region has collapsed to basically a null space, and there's not anything left. And so you'll see it in this chart if you want to quickly run through it. So you just need to fill a response matrix once, and then you can do this sort of trick with OPT to just have it quickly evaluate and solve the linear program. And you'll see quickly where it falls off, at least in the linear sense. And then, God, like Cecile was saying, if things are nonlinear, and they're usually not purely linear, then you might have to evaluate a few solutions somewhere along that place where it actually became infeasible.
And then one more. When using an absolute daring, should I aim to set the value for the increment to be comparable to what would happen if I was using log transformation? Or is there some other guiding principle to follow that I can be certain that my derivatives are trustworthy?
Yeah, so that's an important point in all this. So in the pest world, when we're filling our Jacobian matrix, we want our gradient approximation to be valid locally, right? So we want to take just a big enough step that it's above, say, the noise in the solution. For linear programming, and you can look up some of this stuff from David Offeld and Paul Barlow, generally you need a much bigger increment when you're doing this linear programming thing, because you want to have a big enough increment that you see the relationship at distant constraints, both in space and in time, so that your response matrix doesn't have zeros in it. Because if you have zeros in your response matrix, the linear programming solver thinks, oh, I can do whatever I want. There's nothing here that I'm going to cause any damage with. So you want to have a pretty big increment, especially compared to what you do in the pest world. I mean, so like in this case, we're using multiplier parameters, and our increment was 2. So we were basically doing a 2x increase of the pumping rate on every pumping well whenever we were filling the response matrix. So you generally want really big increments, at least for the early iterations. There's some things, again, from Offeld and Barlow, where they found that as you go along the iterations with SLP, you can actually step down your increment because you're getting into a better region of attraction. And some of that stuff is in opt as well, where you can have it decrease during as the iterations go along, so that you get a more local approximation once you're into a good spot, so to speak. All good? Okay.
Terry did say he'd shut up after that one, but I think keep asking the questions.
Yeah, come on, man. More questions. Anybody questions? Okay, so now it's really going to go off the rails. So now we're going to talk about multi-objective constrained management optimization under uncertainty. So there's a relationship between what we call constraints and what we call objectives. So in the previous example, we said, thou shalt not cause the surface water system to ever become losing. But in reality, decision makers are almost always dealing with trade-offs rather than absolutes. What if letting it become a losing system just for 1 month has some huge economic benefit to the water that could be used? It would be nice for them to know that. Or on the other side of it, what if we left more water in the ecosystem? Maybe it doesn't have a big economic penalty, but it has a huge benefit to that ecosystem. Like that trade-off between these competing objectives. I mean, that's, decision makers, the currency, I guess, I heard this saying once, what was it? Trade-offs are the currency of decision making, right? So that's everything in decision making is about understanding the trade-offs, the gives and the takes. And so what multi-objective optimization seeks to do is to map out those trade-offs, at least the trade-offs we're dealing with in our space, like in our modeling problems. And so let me, I got another cool, I've worked really long on this animation, so I'm going to show it because it took me a long time to make it. This one. Okay, so when you go to a multi-objective problem, though, no longer can you do the linear programming thing. You have to go to a global method because there's no longer a single objective. There's two or more objectives. And so something might have a really great value for surface water groundwater exchange, but a terrible value for groundwater production rates or vice versa. And so you have to use these global algorithms to solve the multi-objective problem. And so this is a visualization of how that population, which is the term we're going to use to represent what was called an ensemble. Now we're going to call it a population of decision variable members. So we have a population, has members in it. The two key steps of these evolutionary algorithms is the generation of a new population and then the fitness evaluation. So we take the existing population and we recombine their members. So we'll select parent 1, parent 2, we'll combine their decision variable values in some clever way to make a child. And we do that a bunch of times and we get this child population, we run it through the model. And then this is where it gets rough. We put the parents and the children together and we pick the best ones. So maybe your child has better qualities than the parents, we would keep the child. Maybe the parents still had better qualities, we keep the parents. And so we just keep doing that. That's called a generation. And over time, through the magic of evolution, we start to evolve our solutions toward the Pareto frontier, which is the best trade-off surface we can find. And that's what we're showing here at generation 88. So after 88 generations of make a child population, run it through the model, put the child and the parents together, compare, keep the best, do it again, do it again. You just keep running this thing, and eventually it evolves towards the Pareto frontier. And so I wanted to make a couple of comments about the shape of the Pareto frontier. So once you're on this Pareto front or Pareto frontier, you can no longer improve one objective without sacrificing something in the other objective. So if we're at some point down here, and let's say we want higher quality, well, we can't just go across in the X direction. We have to go up a little bit, which means higher quality is going to cost more. Or if we're over here and we're like, oh, this is too expensive, I don't want to spend so much, we can't just go down in the Y. We have to also sacrifice our quality to go down. And so these two limbs of the Pareto frontier, this is sort of the classic shape. This lower limb, I would call that the easy wins. Because down here, just for a marginal increase in cost, you get a big increase in quality. So drilling one additional well could get you a lot more performance out of your pump and treat system, say. But once you're up on this limb, this is the one I think we're all more familiar with, and this is diminishing returns. Right? We've over-designed the system once we're up here because just to get a little bit more quality in X is a big step in Y. So we're spending a lot more money just to get that last little bit of quality out of it. And so giving this type of this chart to decision makers, I think is really where a lot of decision makers are hoping modeling is going for them to help them understand these types of trade-offs. And so that's the basics of a Pareto frontier. Do we have any questions, conceptual issues about multi-objective optimization? If not, then we will quickly move over to this notebook. So this is the first MOU notebook. And so we're using that same pest interface. We're setting up all of our little options and variables, just like we have all along. There's some nice text here that Rui added so that people can follow along nicely. Let me go run this thing, and it makes an enormous number of files. And that's because as we're going through each one of these generations, maybe we want to track what the best solutions are doing, what all of the solutions are doing, both on input, on decision variables, and on constraints and objectives. So it's writing out all these files as it runs along. Eventually, we get down to where we can make a plot. Whoops, don't do that. Where was I? Over there. There we go. Sorry, everyone. I'm going to zoom out just a little bit if I can. Let me zoom out. A little bit more, a little bit more. There we go. So here we're plotting our two objectives, and our two objectives in this deterministic case were the cumulative volume of water that goes from the groundwater system to SFR, and the cumulative volume of water that goes from the groundwater system out through the groundwater extraction wells. And so those two are competing with one another because water that would normally go to the surface water system is now going to wells, And so as we pump more from the wells, less water goes to the surface water system. And this is the shape of that trade-off, at least in this Freiberg model that we have. And this is, again, something powerful you could take to decision makers and show them and say, look, if you guys want to pump, look at this one up here. If you want to pump this much more, or sorry, if you want to pump this much more water from your groundwater extraction wells, you can expect to have this much less water coming out of the SFR network, or vice versa. If you want to keep the ecological flows high, well, we're going to have to use this much less water. Sweet. There's your trade-off surface. But what about all that uncertainty talk, right? Well, it turns out you can use uncertainty analysis also with multi-objective optimization. And so now this is where it gets really fun. We take our stack, but we have a population. So we have an ensemble of parameter values, but we have this population of decision variable vectors. That means we potentially have an enormous number of model runs to do. If we wanted to evaluate the chances at every one of those members, that means we need to run the full ensemble at every one of those members for every one of these generations, right? So that's like an insane number of model runs. And you guys may have thought this MOU2 notebook ran for a while. It could be much worse. Briok and I have seen it much worse. So we can make some shortcuts with MOU. It can run the stack in one place, say at the center of the decision variable population, and then just share those results. And I think that's what we're doing in the notebook to prevent doing way too many model runs. But what you can do with the MOU space then is you can say, you know, that risk value, rather than saying I want it to be 95% risk averse, let's just treat risk itself as an objective, and we want to drive that objective to be risk averse. So we're going to say, okay, we want SFR to get as much water as it can. We also want well to get as much water as it can. But whatever we do, we want to make sure that the solution we come up with is reliable, that that's actually what's going to happen when we go out into the field and operate our groundwater pumping system. And so that's what risk as an objective does for you. It brings it in just as any other objective, and it treats it just like the others, and along you go, and you get to make cool looking plots like this. So in this case, we end up with this cool population with this nice rainbow color. As we shift back, I'm sorry, if we want to be risk averse, if we want to make sure that the solution we're going to build is going to happen, we have to sacrifice both quality and cost. So we have to move up and to the left. And that's what this is showing. These are the risk averse solutions where we have lower quality on the x-axis and lower cost on the y-axis. And so that's coming from risk neutral, which was green, which is more this way. So we've had to sort of sacrifice on both axes to get an increase in reliability. And I think that's what we end up showing in the MOU2 notebook. So if you run all the way through this thing and your computer made it, this is sort of the plot to focus on. And so what we're showing here is that as risk gets higher, we go this way, right? So we were here originally, like risk neutral, but because we want to make sure that the actual trade-off between SFR and well is what's going to be observed when we go into the field, we have to move this way. So we have to actually leave more water in the groundwater system, both away from well and away from SFR. And so this is the nature of constrained multi-objective optimization under uncertainty. Any questions about these two notebooks? Okay, if that's enough of that, I wonder if we could get some discussion from Cecile about her experiences with all of these types of workflows.
Yeah, sure. So I learned how to use these tools before the GMDSI notebooks existed, and some of like PayMU's pest from utility and everything. And so I went really progressively. So I started just learning how to use FlowPy and PayMU and how deterministic calibration works with pests. I learned about linear uncertainty analysis. And then I moved on to the whole new world of management optimization. So what's management optimization? What are chance constraints? How to use pest VB opt. And then once I was comfortable with deterministic calibration and management optimization, single objective management optimization, then I moved on to ensembles. So to IES, I moved on to multi-objective optimization. What is a Pareto frontier? How do you do multi-objective optimization with PEST PP MOU using parameter ensembles? And so I think it seems a little overwhelming, all of this stuff, but I think it's important just to go progressively, just to learn the basics of before adding layers of complexity all the time. And so when I moved from one PEST plus, I don't know, software package to another. So for example, from PEST to PEST IS, or from PEST PP Ops to PEST PP MOU, I was reading the reference paper and then reading through the PEST plus manual, and I would go see if other people, like researchers, had published papers where they used those tools, and then if they shared their code, I would go dig through their code. And so I think it's what's nice with sticking to PEST is that so that at least even if there's new theory to learn, the input and output files, the structure is the same. You can still use PyEmu. So I think learning all these new things is a little more straightforward by using PEST++. And I think now that these GMDSI and Jupyter notebooks exist, it's easier to find information. I was just digging through everyone's GitHubs, trying to find examples of code, and now it's all grouped in one place. So yeah, when I was learning about this, I also signed up to every possible users group that I could find, and I was looking through all the issues, all the keywords. When I was really stuck, I posted several issues, even though that was very scary for me. And yeah, that's how I've been learning how to use these. I also had, I was lucky I had people that could explain to me how PEST works, how PyEmu and FlowPy works. I had people that I could go to for questions about coding, and I had time to learn about this. I was doing this when I was getting my PhD, so I had more time than, I don't know, maybe if I was learning about this in a consulting company, I don't know. So that's how I've been learning about these tools. I'm still learning a lot. I think moving on from history matching, so data assimilation to management optimization for me was a really big step. And I think the 2018 paper on PEST BP Ops did a really good job of explaining how you, what are decision variables, what are constraints, and how you can think of optimization. I can move on from history matching to optimization.
Just to give a bit of context, what was the sort of time frame that you did that learning in? Talking months, years?
2 years to yeah, 2.5 years, where I started with I had never I've never coded with Python, never used PyEmu, FlowPy, PEST, and then I moved on to IES and MOU.
That's almost a postgraduate degree in PEST.
That's it.
Yeah.
I feel like adding that, Cecile, you mentioned that you were scanning through the literature, looking for where IES is yet referenced and used. Should probably point out that if anyone's looking for good literature references for where OPT and MOU have been used, there's 2 very good papers by Coulomb et al., which I'm just posting in the chat now. So that, I mean, they are like they're kind of the standard references, I think, for using opt and MOU in the real world.
That's it.
So I would encourage everyone to check them out. Is that HES one published yet, or is it still in discussion?
It's in discussion, yeah. But I spend so much time digging through other people's papers, trying to see what parameters they set, that I think it's nice that then when you're doing it, that you can, if you can detail as much as you can all those steps or share your code, it helps other people a lot. Like, so.
Did you actually, this is sort of a bit of a side question, but did you actually find a lot of people that posted their code and that you were able to replicate what they did, apart from Jeremy and Briok?
Well, Jeremy's code was useful for AUS, MOU. I was working on seawater intrusion, so I was just looking on GitHub for anybody that had used SWI, and I actually found even it was one repo, but it actually helped me a lot. So even one repo can make a difference.
Especially when it's well documented, like Paimi, right?
I've seen worse.
Awesome.
I also learned, moving to management optimization, that you have to be really precise about what you actually want to optimize. Because when I started, I wanted to optimize pumping or optimize groundwater management, but that was actually really vague, because even if you want to optimize pumping in a well field, there are many ways to do that. You can want to maximize pumping rates, but respect certain stream flows. You can want to minimize costs. You can want to do both. So you actually need to sit down and really think about what you really want to do. And I think that's something you define also with clients or stakeholders. And that's a really important part before you start your management optimization.
I think that's actually a really good point. And it's one of the big advantages that I see about actually taking an OPT or an optimization path rather than run a scenario path. So often you'll find that your stakeholders or your client or whatever hasn't actually thought about what it is they really want. And by having to quantify all of that so that you can design your optimization problem, it actually forces everyone to go through that process. And I think that's actually quite powerful.
Yeah.
Well,
that was awesome. Thanks.
That
Cecile.
was. Thanks, Cecile. Any more comments or questions? Would anybody else like to unmute themselves and complain or make comments? Briok and I talked about maybe reconvening this group like in a couple months or maybe longer, just to sort of see like a long-term check-in to see where everybody is, see how everybody's doing, see if you have new questions or comments. Would anybody be interested in such a thing?
Two thumbs up.
2 thumbs up. There we go. 3. Yeah, so I mean, I think that would be a bit interesting. Because I mean, it's going to take time for everyone to adapt to what we're doing with the GMDSI notebooks for your specific problems, and maybe a couple months, 3 months down the line, you'll have an entirely new set of questions or issues to discuss. Well, what should we aim for? January? Is that too far down the line? Does anybody have a preferred meetup date? After the holidays, maybe January?
January works for me.
Okay. All right. Well, I guess we'll just send out an email. Yeah, I'm flexible too. So and again, if anybody comes up with questions, issues, problems, please post those on GitHub. Like we're actively monitoring those and trying to respond as frequently as we can. And if there's no more questions, then I think we might have to wrap this thing up.
Who'd have thought MOU would be the the shortest of the session.
That's right. All right. Well, thanks everyone. This has been a lot of fun. I hope you guys found it useful. I know I had a good time with these sessions. And you can always email us, but GitHub, I think, is the preferred contact method, if you don't mind. And we'll see you guys in a couple months, I guess.
And fill in Rui's questionnaire if you've not done it already.
Oh, yeah. The questionnaire, correct. Sweet. All right. We'll talk to y'all soon.